Bonjour à tous. Hello, everyone. Nice to have you for this workshop with us today. We are the company GERB, and we will present you with 3D seismic protection for SMR structures of our company GERB. My name is Julien Bastet. I am Managing Director at GERB France, and here with me is Daniel Siepe, who is Director at GERB in Germany, and he is as well head of our seismic protection department. So, after a quick introduction, we will talk about modular concept today and project examples and about our solutions at GERB. And then we will conclude this workshop. So, just so you know, at GERB, we are specialized. We've been specialized in seismic isolation and in vibration control for more than 100 years. So our solutions are based on what you can see here on the screen, which is spring units. Spring units on the left side, and viscous fluid dampers on the right side that you can see here. So we are very specialized in this kind of solutions, and we are even considered as leaders in these solutions for seismic isolation and vibration control. So our application areas are not only industry and nuclear, but construction and infrastructure is something we are working on. So for example, we can isolate whole buildings against either seismic inputs or against trains in the neighborhood that would disturb the buildings. We can as well isolate, here as you can see, footbridges against the swinging effects created by the people working on it. Second big application area for us is the transportation in the trains. And so we have special solutions, spring units and dampers, so that we place on the track bed so that it prevents the excitation and the vibrations from propagating into the neighboring buildings. And then, of course, industry and nuclear applications, and this is what we will talk about today. So, how does it work, our products, our spring units and dampers? What's the principle of it? Well, here, for example, we have pumps and a fan, and these are rotating machines. So this creates vibrations, and we want to prevent these vibrations from propagating into the surrounding area. So we place these machines on our devices, and because our devices are really low frequency equipment, then it makes an efficient isolation of the vibrations and preventing everything to vibrate. So we have here spring units there. So please note that our color is yellow. So this is specific to GERB devices. So then you know when you're looking for our devices, you just look for the yellow color. Another example of what we can do in industry, engines we can isolate. You can see that on the left side of the slide, and even big presses. So just to tell you how big it is, just have a look at the people here. So this presses, it forms steel pieces, and so we have spring units below it to isolate the machine. Another example, which is quite impressive, this one as well. So hammers, we can isolate forging hammers against the effects of the impacts. And here you can see the spring units there, yellow again. And here we have an example of a huge pit that will, where a hammer will be on it. So you can see the size of what we can isolate and what we can handle. Now a picture of a building so that you can see how it works, the isolation of buildings. So we completely decouple the infrastructure from the superstructure. Here you can see, yellow again, our devices, so that even with earthquakes, there is no problem. The building will be safe and will be robust. Once again, a building here, but another type of building, and we like to present that because it's WNE, of course, spent fuel pools. So you can see our device is below the concrete pool, and these have a great interest to mitigate drastically the seismic input. So with that, you can lower the accelerations that happen in the pool, and this way you create something which is completely safe and completely robust for the pool against the earthquake. And at last, another example, because we can even have the isolation of a whole reactor, for example. And here we can see the earthquake happening. And you can see and understand how it works, the decoupling of the structure, and how the structure is then safe and robust. So once we have talked about all these different cases, now let's talk a bit about the current situation and the challenges and what is at stake. So first thing I think we can all agree with is that seismic requirements are getting more and more severe. So it's not new, it dates back from Fukushima, of course. And it is more and more true. The seismic inputs are more and more important. And we have to deal with that, whether we are designers or constructors in a nuclear domain. Second is that, talking about the SMR, these are serial production. And it requires standardization. And this is based on the most demanding seismic site. So these two parameters mean that the seismic inputs are very big, and we have to deal with that. That's the consequence. Strong need for reliable and efficient seismic isolation solutions. And that's where we are efficient to do so. We are able to sustain big earthquakes and to dramatically make these accelerations lower. And then I will let the field and hand over to my colleague, Mr. Siepe, who will develop a bit more about our solutions.
Okay, thank you very much, Julien. Good morning also from my side. As mentioned already by Julien, we are talking about a 3D system. So what does it mean? So if we have a rigid structure, we get 6 degrees of freedom. So we have 3 translations and 3 rotations. And if we place a structure, for example, of a 3D device, we get a vertical mode shape, we got a rotation about the vertical axis, and we got 2 rocking modes and 2 pendulum modes. And just to highlight it, so 3D, it's not just 2D plus vertical. Someone might get the idea to combine 2D seismic devices with vertical devices. This is quite complex. But with our spring elements, since more than 100 years, we are always in the 3D world, and we are very familiar with the consequences. So starting to talk about frequency, we always would start with a vertical frequency, with a vertical support of a structure. Could be machinery, could be equipment, could be a reactor or a nuclear building. So the spring elements are linear devices, so you can easily calculate the vertical frequency, but you can also calculate the frequency by just knowing the vertical displacement of the spring. So let's take an example. You have a mass sitting on springs, and vertical deflection of 40 millimeters equals vertical frequency of 2.5 hertz. And this needs to have it in mind if you talk about frequencies, that there's a direct connection between the static deflection of the spring and the frequency. And you can imagine if you want to go to very low frequencies, you would need a quite large vertical displacement. So in the end, you have to find an optimum between the frequency, damping, and the capability of the structure. So just to show you some examples, we developed, used, and implemented more than 2,000 different types of springs. So it could be a very small spring for small load, very big springs for buildings, depending on the weight, on the requirements. And so we have a wide range of capacities. We have always 3D. In some cases, it might be not required, but we benefit from it that we can adjust the parameters of the springs to the project-specific requirements. The elements are linear devices, so quite easy to calculate. If you have to do some calculations, it's quite straightforward. And there's no change between static and dynamic characteristics. So together with the spring elements, if it's a higher seismic event, we always would combine it with damping. So the springs make the structures flexible in horizontal and vertical direction. And with the 3D damper, we provide damping in horizontal as well as in vertical direction. So if we combine springs and dampers, we get a 3D system. Also here you can see we may have smaller devices and also quite huge dampers if we are supporting nuclear building structures or very heavy buildings. So we have a building, this one has a weight of 300 tons, but the largest building we are supporting on springs has a weight of 200,000 tons. So this is not a nuclear building, it's a theater, but it's in the same range like a full nuclear island, for example. So we have a high level of confidence that we can also support building structures in the nuclear industry. And there are some ongoing projects for SMRs, projects with US companies. So small modular reactor, so modularity is already a part of these developments. And so the modular concept, I think it's quite easy. We don't need to explain it in general, but we adapted it to the seismic isolation system. So as we use different devices, so we have the spring elements to provide load bearing and to provide flexibility. And we have damper devices to provide the damping. And you will see on the next slides how you can use these devices to modularize your approach if you are, for example, considering a structure to be located in several different seismic sites, for example. So if we start to look at the spring level, you can think about, okay, we have spring elements. We can choose different numbers of springs inside the element. We can choose different numbers of elements. So you see there's a wide range of modular design targets that we can address with it. So if we have different loads, we may use different elements. If we have a different weight, we can simply add or reduce numbers of elements, or we even choose different numbers of springs inside the element to address the modularity. And with the damper, it's quite similar. If we have a structure in a low seismic zone, we may use maybe no damper or only several of dampers. And if the seismic requirements, for example, are increasing at different sites, we can simply add numbers of dampers. So as we distinguish between flexibility and damping, you're quite free in the choice of selecting these elements. And if you have your project in a higher seismic zone, you can simply add more dampers. As a different possibility would be to also mix and match different type of dampers depending on different site-specific or project-specific requirements. So some years ago we started also to provide a little bit more publication about typical development steps, how to do the layout of a 3D system, because we realize that it's not that straightforward for everyone. So if you are interested in this, please have a look at our presentations or feel free to contact us to get a little bit more information how easy it is to start with a layout of such a system and see the benefits in 3D. So we also want to show some project examples. So in nuclear power plants, we have projects. We are in the field for more than 40 years. You can find our solutions, for example, at very important machinery, for example, emergency diesel generators. There we use the spring and damper combinations for seismic protection and also for protection against high shock loads, for example, due to aircraft impact. And also vibration isolation, it's already always included in the solution. We use it also, as mentioned by Julien, to support a spent fuel storage tank. This is an example from a nuclear power plant in Switzerland. And we have more than 400 buildings sitting on our spring elements, most of them for vibration isolation because they are close to a tram or railway, but there are also examples for seismic protection. And also, let's say, in the equipment area, a lot of parts of substation equipment, transformers, capacitor banks, air core reactors are using this technology for seismic protection. One initial study we did to show the effect on a nuclear building, so we compared the structure with and without springs and dampers. So first of all, you get a significant reduction of accelerations. Here you can see over the height of the building how much reduction is possible. So you are reducing the seismic accelerations as well as internal forces. Furthermore, you also help the design and qualification of internal structures, internal equipment, internal machinery, as the system reduces the in-structure response spectra in horizontal and in vertical direction very efficiently. So not only the building structure itself benefits from the reduced seismic input, but also, let's say, if you have to qualify your pump, your pipework system, or electrical cabinet, you benefit from the support of the whole structure. This is also something investigated by third parties who are getting more and more interested in our solutions because one of the main advantages is that we are talking about 3D. We do not only have a 2D horizontal seismic protection efficiency, we have a 3D efficiency. And you can also see if we compare results to typical 2D systems, we are very good and quite similar in horizontal direction. There are some peaks at the 2D systems, but if you look at the vertical direction, you can even see some areas where the 2D solution is even worse than the unprotected solution. And this is something which needs to be considered and investigated so that we always have in mind that we are talking about a 3D world and we have to investigate all three directions. So let's come to some conclusions. So you see on the right side one example of a test where we tested at full-scale devices for a nuclear installation, spring units, dampers, and you can see here also a very important type of machinery, emergency diesel generators in a nuclear power plant. So in this business we have hundreds of examples of motor engines, and in nuclear power plants there are some examples where these structures are spring supported for 40 years. The elements are maintenance free, so you don't have to exchange them, and you even have the possibility, if there are increasing seismic demands, that you can check and maybe update the solution. So the elements are used to support the weight of the structure, and the springs provide the necessary flexibility. With the dampers, we achieve horizontally and vertical damping, and we can, having in mind this modular idea, we can adjust type and numbers of springs, and also we can adjust the numbers of dampers, which is quite a nice feature because the scope of work of the elements are clearly distinguished between dampers and springs, so you are much more flexible if you have a structure that is intended to be placed at several locations worldwide, for example. And of course, the whole system has to ensure its proper function over the lifetime of the project, and this is well done. And as already mentioned, we have a lot of experience how to do the layout, and we would be happy to support you for your projects. Okay.
Well, thank you, Daniel, for these explanations. I will conclude about our presentation. Oh, it's you. Yes, that's the one. So I will conclude about this presentation. So I said previously that what was at stake was that SMR required reliable and efficient seismic isolation solutions. And here I want to summarize all the advantages that Daniel explained. First, our solutions, GERB solutions, are efficient, and they're efficient in 3D direction. This is really important. We're a 3D solution, and with the efficiency that comes with it. Second, our solutions are adjustable and can be replaced. So it's not just solutions that you leave in place, you can adjust them. And we know that the lifespan of nuclear power plants, they require that it has to be adjustable, and we can change the spring units and everything. This is very important. Third thing is that our solutions are operational. I mean, we're not talking about things that just exist on paper. It's real. We have hundreds and hundreds of references, and so we are very confident about the fact that our solution works in real life. And then at last, we have the experience, we have the knowledge and the qualified staff to accompany you on your projects. So let's work together. We're done with the presentation. If you have questions and comments, we'll be happy to answer these.
And just a side note, just luckily, if you are interested in to see and touch a real spring element, our booth is just behind the corner. So we would be also happy to welcome you at our booth later. So thanks also from my side.